vector projection. And you have a vector V, which is equal to V1, V2, V3. Now I'm talking about vector in a three-dimensional space. Then you have another vector A, well, a little longer. This is A, which is equal to A1, A2, A3. Three-dimensional space vector. Now this is the angle theta, right? And you have a perpendicular line. This is a vector projection of V onto A. That is notation. V projects onto A. Okay, this is the vector, right? We are more interested in the length of the projection. So we are more interested the norm or the modulus of this projection V onto A. This is the length of this vector, right? According to this triangle, this is the modulus, the norm of V multiplied the cosine theta, right? So this will equal to norm modulus V times cosine theta. Okay, that's good. Now, if we multiply the norm of A divided by norm of A, that will be equal, right? Still equal. But the numerator is A dot V, the dot product. Denominator is the modulus, the norm of A, right? Now we take absolute value because the distance is always positive. So that is the formula to find the length of a projection vector from V onto A. Very easy to calculate. It's very useful to apply for solving the questions in three-dimensional space, like the distance between points and the plane, between points and the line, and the distance between planes, the distance between points and the between lines and the plane, or the distance between straight lines in the free space. So this is a very useful tool to find the distance in three-dimensional space. Okay, let's find examples. Okay, we have a plane. We have a plane. This plane has equation, right? The x minus, say, for example, 2y plus 3z is equal to 5. Okay, this is the plane. That's the equation of plane, right? And we know that the equation plane shows the normal vector of the plane, right? This is a normal, say, okay, this is a normal vector. The normal vector is equal to 1 minus 2 and 3. Okay, this is the normal vector of this plane. which means the vector perpendicular to the plane, right? Now, suppose we have a point somewhere, say the point is, in a space, right? Say this is a P. P is, any point, say 3, -1, and a 2. Okay, that's the point, P. We want to find a distance from P to the we want to find a distance, right? This is distance. We want to find a distance. Let me use the red pen. The distance, right? D, between point to the plane. Now, there are several ways to find it, right? But I don't want to mention those methods. You know how to find the distance between points in the plane. But here I'm using the projection, vector projection, shows that it is very convenient and very easy to find the distance. Now, how to find the distance? I choose any point, choose the point, say I choose this from this equation, right? How about x equals 5, y equals 0, and z equals 0, right? So this point satisfies the equation of the plane. So the point is the point is in the plane, rather. I named this one as a Q, okay? So QP is a vector. QP is a vector. 3 minus this one is -2, right? This minus this one is -1, and 2 minus this is 2. Okay, this is the vector, right? And then we project this vector onto the normal vector of the plane. So that will be perpendicular, right? And this one, this point is perpendicular. So this is our distance, you know. This is our distance. Well, actually, you can move the vector, normal vector, passing through P, you know, because the vector is as long as you have a length and direction, it doesn't matter where's the location. Now, okay, so we can find the D by the projection of a QP onto normal vector N. Then it is very easy, you know, the projection of QP, right, onto normal vector, absolute value, that is the absolute for distance, is equal to absolute value, the QP, which is -2, -1, and a 2, dot product of a normal vector, 1, -2, and a 3, divided by the norm of n, right? The modulus is 1 square plus 2 square plus 3 square. So this is equal to this is 149 well, this is 14, right? Square root 14. Yeah. Okay, then this is equal to -2 plus 2, this is equal to 6, right? Okay, so that is the distance, you know, very easy. Very easy to find the distance. Now, suppose we have you choose a different point. Suppose we choose another Q, say this Q is choose another point on the from the plane. Say what point? Say the x equal to 1, y equal to -1, z is equal to no. This is 1, z equal to 1, then x equal to 0. Okay, 0 minus 1, 1. Satisfy this equation. Therefore, that is the point in the plane. Now then we have a new QP. New QP is QP is equal to 3 minus 0 is a 3. Minus 1 is 0. 2 minus 1 is 1, right? So that is my new QP. Then we project this QP onto normal vector. Okay, this is this, and this will be this. So this is my distance. So this projection of a new QP onto normal vector n, absolute value, is equal to absolute value of 301 dot 1 minus 2 and 3. Okay, divided by the 1 square, 2 square, and 3 square. So this one is equal to 40. This is equal to 6. See, you got the same value. Same value. So what I mean that doesn't matter which point you choose. You project this vector onto this normal vector. You have always same value, which is the distance from point to the plane. Okay. So now you may practice by choosing any other points in the plane, and you will find the same distance. All right. Okay. Okay. Let's change a question, and we are looking. You have a straight line. The straight line is passing through point 2, 0, and minus 1. And you have a directional vector v, which is equal to 2 minus 1 and 4. Okay. For straight line, you have a straight line in three-dimensional space. As long as you have a point, you have a directional vector. You have a line. The equation could have a symmetric form or a parametric form. Doesn't matter which form. You see, you have a straight line. And suppose you have a point. The point is 1, 5, -2. All right. We want to find the distance between the point and the line. Now, of course, you have ways to find it, but I find that the projection method is well, maybe easiest method to find it. Now, how do we start? I choose the point. Say this is the Q, and then you have a vector, right? QP is equal to 1 minus the 1. This is a minus 1. 5 minus 0 is a 5. Minus 2 minus 1 is a minus 1. Okay, then you project this QP onto this directional vector. Okay, right? So you have this distance. This is the distance projection of QP onto V, right? Onto V. Yeah, it's very easy to find it. So the projection of QP onto V, well, is equal to absolute value QP, right, dot V, and divided by the modulus, the norm of V, right? So this one is equal to absolute value minus 1, 5 minus 1, dot 2 minus 1 and 4, divided by square root 2 square, 1 square, right, 4 square. So this one is equal to 2, 5, 4 is equal to 11, right? 11, yeah. This one is equal to 4, 1, 16 is 21. Okay, that is the distance of the projection vector. But we are looking for this. We are looking for the distance between P and the straight line. Therefore, we are using Pythagorean theorem. So D is equal to square root, right? Square root. The length of this is QP, right? The length of QP is equal to what? Is equal to 1 square, right? 5 square and 1 square. That is the hypotenuse square minus this is square, right? 11 square over 21 minus this is square. Square root, you get distance. So this one is equal to well, I hate arithmetics. Well, this is equal to 27, right? Minus 121 over 21. So this one is equal to 21. I calculated it was 446. But it's not important. It's just a number, right? So this is the distance between the point and the straight line. Now, of course, you can choose any point. Now, let me choose another point, just for fun, you know. Choose another point. How to find this point? So this equation is that x minus 2 equal 2t, right? Y equal negative t. Z plus 1 equal to 4t. So when t equal to 1, this will be equal to 4, right? Minus 1 and 3. Okay, so if we choose this as a Q, not this one, then we have a new QP, right? New QP is equal to 1 minus 4 in negative 3, and 5 minus 1 is 6. Minus 2 minus 3 is minus 5. So we get a new QP, right? Then the projection will be this. Okay, the projection of QP onto V will be equal to this one dot one, right? This one dot one is minus 3 is minus 6. 6 minus 6 minus 20 absolute value And this is the same thing, right? Same thing as 21. Okay. So this one is equal to 32 over square root 21. Well, anyhow, these are just tedious calculations. Then we're looking for t, right? D. D is a square root QP, new QP, 3 square plus 6 square plus 5 square minus 32 square over 21. Well, believe it or not, this would be equal to 32 over 20. Same 4 for 6, sorry, it's 4 for 6. Okay, the same value, it must be the same value, right? Okay, so this is not important, just tedious calculation. What I want to say is that this projection method is very easy to find a distance. No matter which point you choose any point. And usually we choose easiest to calculate the points. You can choose other points this side. Okay? Doesn't matter. You get the same answer anyhow. Okay, this is the question, the distance between points and the line. Now then you can apply this into, for example, two parallel lines. We want to find a distance. You just pick a point on one line. Then you use this method, you find distance, right? And for example, you want to find the distance between points and a plane. Then you pick up the points in the line. Then you find distance between the points to the plane. Then you find a distance. Okay. Let me do another example, which is the distance between skew line. That is this is the maybe a difficult question for many students, in learning the vectors. Okay. So suppose we have two lines. These two lines are skewed, skew line. Skew line means they are not intersecting, they are not parallel. And what is this line? Say this line is a given point, or 2, 1, and 1, having directional vector 4, minus 1, and a 2. So this is the line passing through this point, having directional vector this, right? And this is this is another line having directional vector, say 1, 2, 2. Well, I choose the easy number, right? And this is a -1, 3, 1. Okay. We want to find the distance between these two skew lines. Now, the key is that you must find a vector which is perpendicular to both, right? To this one. And that will be the distance. That will be the distance between the two lines, right? Yeah. Okay, how do we look? Using projection is very easy to find it. For example, I choose the point, well, because this point is given. I use this point. This point is given. Then this becomes a vector. This is 1, huh? This is a Q, this is a P. Okay? Then you project project this one onto this vector. This vector is n, right? Then you get distance. Because this point project to this line will be here, and this point project to the perpendicular line will be here. So that will be distance. Okay, let's find everything that in detail, all right? How to find this n? N is a vector perpendicular to both of them, right? Both this and that. So this is a 1, 2, 2 cross product 4 minus 1, 2. Okay. So this one vector is equal to, delete this one, minus 4 minus 1 is 6. Delete that one. This one minus 1 is 6. Yeah. Delete that one. And then it's minus 9. Well, you may use your way to find the cross product, right? Yeah. This one is 8 minus 2. Yes, it's correct. So I can simplify. This one is the same as divided by 3, right? It's 2 and 2 minus 3. So this one is a 2 and minus 3. Very easy to find. Okay, you may verify. This time this one must be 0 because they are perpendicular. This one time this one must be 0 because they are perpendicular. Easy to verify, no? This is 2, this is 4, this is 6. This 6 is 0. This is 8 minus 2 minus 6 is 0. Yes, therefore this is right. 8 minus 6 is correct. Now, then the distance d is equal to the projection of QP onto n, absolute value. Okay, this one is equal to n squared is 4 plus 4 plus 9. Well, let me. This is QP, right? Where is the QP? QP is equal to this minus this one is 3. This minus this one. This minus this one is minus 2. And this minus this one is 0. Okay, this is 3 minus 2, 0, dot 2, 2, 3. Absolute value. This one is equal to square root 17. This is 6, 4 is 2. Okay, this is my distance. You know, it's really very easy to find. The distance between two skew lines is not an easy question, well, for many students. But look, this calculation is so easy, so straightforward. Okay, but just for curiosity, you know, let's choose other points. Okay, choose other points. Say, choose a point here. This is a Q. You know this line, right? This line is x plus 1 is 1t. Y minus 3 is a 2t. Z minus 1 equal to 2t. Therefore, when t equal to 1, or you can find the Q is 0, 5, and 3. And similarly, you can find P, right? P. Well, this is 6, 0, and 3. Well, I'm not going to detail this here. You can find any other points, any points on the line, as long as the points are given, direction is a given, directional vector is a given. So this is my new QP, right? New QP. Then you project this one onto this normal vector. You still get this same distance. Okay, then my new QP is equal to 6 minus 0 is 6, 0 minus 5 minus 5, 3 minus 3 is 0. Okay. Then my distance is equal to absolute value projection of QP onto the normal vector, this vector, which is equal to square root. This is 2 square, 2 square, 3 square, right? 2 square, 2 square, 3 square. And here is a 6, 5, 0, minus 5, dot 2, minus 3. 2 minus 3. Absolute value. So this is 12, 10, this is 2. Yeah, that's a square root 17. You see, you get the same answer. See? I just randomly choose any other. You can try yourself, by using by choosing any other points on the lines. See, no matter how far the point is on a line, when you project, it is always to the foot of the perpendicularity of the vectors here. The distance is always there. Yeah. Let me say it again. Vector projection is a very useful method to apply for finding the distance between points and straight line, or points between the plane, or the distance between the lines, the distance between the plane, and so on in three-dimensional space. Okay, so I hope you like it. Thank you. Thank you for your watching.